All right, so in this video, we're going to show how to do regression in R and some of the features, some of the results that you can pull out of that, how you can use it to make predictions and the like. All right, so let's go ahead and get started here. All right, so I already have loaded in here a data frame that I'm going to be using. So let me go ahead and show that to you. All right, so this data frame, when I loaded it from Excel, I just called it DF. Uh, it's just to make my life easier, honestly. Uh, then then I can just kind of use generic formulas without having to make sure that it's keyed to the specific name of the data frame. Right, so I have in here the Canton unemployment rate and the US unemployment rate. And what I'm going to do, my goal here, is to see if there is a linear relationship between the Canton unemployment and the US unemployment rate. I'm going to treat the Canton unemployment rate as the dependent variable or the response variable, with the US unemployment rate being the independent variable or the explanatory variable. So that's my goal here. So if you think in terms of what linear regression does, right, it is trying to figure out what is the best straight line formula. So the form that I like for that is y equals a plus bx. If you think in terms of algebra, it's y equals mx plus b. It's the same form, just rearranged and renamed a little bit. Uh, so we're just looking for a formula like that that does a reasonably good job predicting what the Canton unemployment rate is going to be as your y based on using the US unemployment rate as your x. So that's the goal. All right. So in order to do this, we're going to use a couple lines here first to run the regression and to see those results. Let me actually minimize that. All right, so the first thing is I want to save the results of the regression, right, in an R object, which I'm going to call lm.r. Now, you don't have to call it lm.r. I just like that. Okay, so the LM stands for linear model, R indicating that it's a regression or that I'm working in R. Either one doesn't really make much difference how you want to interpret that. Again, you don't have to use that name. You could use any name you wish, but I'm going to use lm.r for my case. All right, so then what is important is what falls on the other side of the assignment operator, and that is the LM function. So the LM runs a linear model, right? So in order to make this, I'm going to have to set a few of these, so a few of the options, right? So the first thing we need to do is we need to have the formula. Right? So formula equals. Okay, so in order to do this, uh, the way the basic setup is you're going to do y and then the squiggle and then x, right? So whatever your y variable is, then use the tilde or squiggle that is in the upper left corner of your keyboard, right next to the 1 key. You have to hold the shift to activate the squiggle. So that's the form. Now, what is going to happen now is if I run this, R is going to say, I don't see anything called Y or X. Fair. So what I need to do then is to tell it what variables those are, right? So instead of Y and X, I'm just going to delete those. I'm going to go df $, and then it brings up the list of options. Right? So Canton unemployment rate, US unemployment rate. Well, I want Canton unemployment rate to be my Y. And then, again, use the tilde. And for my X, I want the US unemployment rate. Right. Now, there's a very important step here, and it's a step that honestly made me have to remake this video. It's more significant than what I first thought. And that is, we have to put a comma here, and then put data equals df. That's one step. So that's telling it to pull the data from whatever we call the data frame. In my case, I called it df. The last thing I need to do for this setup is to take this df $ and delete it from the y and from the x. Otherwise, what's going to happen is that R is going to have a hard time associating this this formula with any other data, which is going to be a problem if I want to do some predictions using new data, right? So what this is doing is saying, okay, whatever data you happen to give it, use the formula. Canton unemployment rate, right, is based on the U.S. unemployment rate, right, using a linear model. Now, in order to make that model, we're using the data found in the data frame we call DF. So that's the setup here. Now, if we only run this by itself, we'll get no output because all it's going to do is run that linear model and store it in lm.r. So it'll just create this lm.r, but we won't see anything. So in order to see something, I want to have one more line that is summary lm.r. Right, so that is going to summarize whatever is inside of that. In our case, it's regression results. And so let's go ahead and run that. And here's our output. All right, so we have first the call. Right, so that is just telling you what it was that created that object. Right, so it's the LM formula. The next thing would be residuals. So residuals are the name that we use for errors. So in effect, what is happening here, right, is that R is looking at all of that data that I fed it, is trying to draw the best straight line that it can in that data. But that's not going to fit it perfectly usually. So there are going to be little errors. So then it's taking and looking at those errors to say, well, what do they look like? Those errors are what we call residuals. Right, so what we found is that, say, the smallest residual here, right, so it's negative 1.8. Now it's not smallest in magnitude, that's most negative. The maximum was 3.2338. So we know that uh, so it looks like our range of error can go anywhere from, you know, we're undershooting by about 2% to overshooting by about 3 percentage points. So, since unemployment rates are measured in percentage points. All right, so there's a significant range of errors here, but most of the time it does look like we stay within, yeah, roughly 0.5, 0.6, something like that. So it's our first quartile and third quartile. Our median is right around zero, which is what we'd hope for. The next part is this coefficients table. And so for the coefficients table, you have your list of coefficients. So one is the intercept. So if you think in terms of um, a linear equation, so intercept, right, is if x equals 0, what is y equal to? There we go. And in this case, the estimate for that is 0.38461. The next thing would be the US unemployment rate. That would be not the unemployment rate itself. This isn't telling us the value. Instead, this is telling us what the slope is if that unemployment rate is our x. Right, so in this case, when the US unemployment rate, whatever that is, we take it, multiply it by 1.03894, right, then add the intercept to it to get our prediction. Right, so this slope variable, really, slope estimate, what it really tells us is if the US unemployment rate goes up by 1, how much does the Canton unemployment rate go up? That'd be your answer right here. It's that rise over run kind of concept. Okay, so that's the first column here of estimate. So standard error, so this would be, it gives you some idea of how much error is involved with these estimates. And you can use that then to construct a confidence interval if you want to. So typically, if you have a fairly large sample, and here we do, we have over 300 in our sample, you can take the standard error, double it, and then that's basically your margin of error, right? So say our intercept is going to be 0.38461 plus or minus about zero point 0.3. Or the slope on US unemployment rate is 1.03894 plus or minus about 0.05. Just taking those standard errors, multiplying them by 2, and treating that as a margin of error. The t-values, and so these last two columns are I'm going to really treat together. The t-value and this PR greater than t, that's really a p-value. So those are both based on a hypothesis test, and that is that that particular line's coefficient is equal to 0 is the null hypothesis, right? So this 2.5 for the t-value, and very importantly, the p-value of 0.0126 is based on testing, is the intercept equal to 0 or not? So is the intercept equal to 0? Equal to 0 is our null hypothesis. If we have a really low p-value, typically less than 0.05, then we would reject that. So this is telling us, yeah, the intercept is probably not equal to 0. And then this one, just a reminder of how R will show numbers. If numbers are really big or really small, it uses E notation. It's really just a simplified way of communicating a scientific notation. So this 2e negative 16, it indicates it's 2 times 10 to the negative 16th power. So 10 to the negative 16th power, we're talking about 0.000000000000000001. So 15 zeros before you hit something that isn't zero. In this case, that thing would be, it actually says less than 2, right? So a very, very small number, definitely well below 0.05. Yeah. Now, another thing that you may notice here is that we do have these asterisks here. So what those are telling you, it tells us in the next line here, these significance codes. So you can see where they fall in these various ranges, right, tell you the level of significance. So if we're between 0 and 0.001, then it's going to assign, right, three asterisks there. If we're between 0.001 and 0.01, it assigns two. If we're between 0.01 and 0.05, it assigns one asterisk. Between 0.05 and zero point 0.1, it just gives a period. Anything above zero point zero 0.01, it's going to put nothing there. Right. So one thing you can do, you can play the game of what I sometimes like to call find the asterisks. Right? Anything that has an asterisk one, two, or three, it doesn't really make any difference, would generally be considered statistically significantly different from zero. In other words, what we really care about for us right now is this one. Right. So is there a connection here? Yes. Yes. There's definitely clear, statistically significant evidence that the US unemployment rate does have an impact, right, on Canton unemployment rate. There is an association here. All right. I'll list a couple things that we can look at. One would be the residual standard error. That's really just it's based on what your standard deviation is for your residuals. This is mostly useful in coming up with prediction intervals. Right? So when you make a prediction, which we will do here in another step or so, right? When you make a prediction, you can just apply the formula. Right? So intercept, right, plus slope times whatever your x variable is you're trying to use to predict the y. Right? You can do that. You can use the simple calculator for that. But the problem is that we know that there are errors around that. That's what the residuals up here tell us. Right? And then the standard error can be used, right, to come up with, well, what is the interval around that prediction that we're pretty sure we're going to be within. Okay. The next thing would be the r squared, which here it reports two. One is the multiple r squared, which is uh, just kind of a basic measure of how well a straight line actually describes the data. I'll get in more detail here in a second. The difference between multiple r squared and adjusted r squared is that adjusted r squared penalizes you for adding uh, x variables. So each x variable you add is going to lower your adjusted r squared, even if it doesn't lower your multiple r squared. And that's really just to prevent you from saying, well, let's just try to throw as much stuff into the model as possible to try to get that r squared up. Because it's only going to get better by adding more stuff. You will not have it get worse. But you end up then feeding a bunch of data into the model that is just junk. So it's just taking extra time to do the math, even though the math isn't adding very much. All right, so what does this actually mean, and how do we interpret this? I'm just going to focus on the multiple r squared here, this 0.854. Oh, it's 0.8254. That's it. Right. So what this means, right, is that we look at how much variance there is, right, in your y variable. So in our case, in the Canton unemployment rate, and there's going to be some variance there. So the question is, right, does this straight line we're drawing there, does it help to explain that variance? Right. So we're looking at how the overall variance between just what the y values are in their mean, how does that compare to the y variables versus this line that we have drawn? So if we have a multiple r squared of 0, that indicates that the line added nothing, which normally that happens in one of two cases. That would be one, that is that if we were to plot this out, so have x along the x axis, y along the y axis, and just plot all of the data points, it would look like what we call a cloud. That is that there is no obvious pattern. It doesn't look like it's generally going upward or downward sloping or anything like that. It's just it's just a bunch of random points all over. In that case, drawing a straight line in there is not going to help us, right? So we'd have r squared of 0. Another case, though, is if there is a relationship, but a straight line doesn't do a good job capturing it. So especially things that are, say, U-shaped or V-shaped, those are going to have an r squared around 0 as well, because you try to draw a straight line through it, it's going to end up either, right, you're only capturing one side of the V or U, right, or it's just a flat line going through it, in which case we're not really explaining anything. A flat line indicates no relationship, right? So in this case, it's not that there isn't a relationship, it's that relationship is not a straight line. Now, if you have a perfect straight line, so if you plot out all of the data points and they're exactly in a straight line, you can draw a straight line that goes right through, exactly through every single point. In that case, you'd have an R squared of 1 because it's perfectly explaining all of the variation that you see in your y variable can be explained by that straight line. So you're going to have a number somewhere between 0 and 1. What is good and what is bad very much depends on the context. Right? So think of it this way. Suppose that I am running an experiment in a physics lab where I'm trying to see, right, how, so I have, say, a vehicle or something like that, and I started off at some initial velocity, and I want to see how far it travels along a track. So this is something where I might possibly expect there to be a straight line relationship. That'd be reasonable. And I have very tightly controlled lab conditions. It's always going to be the same car. I make sure that, say, I lubricate it every time or whatever to make sure that, you know, we don't have friction building up or something like that. Right? I make sure the track is in the same condition all the time. So I'm controlling all of the variables except for that velocity. That is the thing that I'm also controlling, but I'm varying that intentionally. So in this case, I would expect the R squared to be extremely high, very, very close to 1, probably zero point 0.9 or higher. Because the one variable that I'm changing, I expect to explain all of the difference that I see, right, in the thing that I'm trying to observe. So how far we get, I expect that to be completely explained by the changes in velocity. Now, on the other hand, when we have natural data, especially social data, where there are lots of variables out there that can affect the way people behave, right? So most business data works this way, right? So whether or not you make that sale, right, will depend in part on the things that you as a business control. Will also depend in part on things like how well did the person sleep that night? Right? This is not something that you have control over, right? Did they have an argument with their spouse? Right? All of these things can have an impact on business decisions that people make, even though it's not something that we can control or observe. Right? So in that case, there are a lot of variables out there that will have an impact on whatever our y variable is we're trying to explain, right, that we just can't capture. Right? So in that case, we can really think of this multiple r squared. You can think of that as what percentage of the variation in your y variable can be explained, right, by your x variables. So with natural social data, 30% might be pretty good, right? So multiple r squared of zero point 0.3, that could actually be pretty good in some cases. So in this case, we're talking about what is it that's going to have an effect on the Canton unemployment rate? Lots of things are going to have an effect on that unemployment rate. Some things local, some things national. So what's really happening here is that we're finding that those things that have an impact at the national level and affect the US unemployment rate also seem to have a very strong effect in Canton as well. So that's why we see a very high R, multiple R squared here, given that this is social data. And so 0.8254, this is a very strong relationship as far as I'm concerned. The last line then would be this F statistic. And so the F statistic, first, I would not put a lot of weight on the exact value of this F statistic here. That number is very difficult to interpret because it's going to depend on the following numbers, these two, which are your different degrees of freedom. So I would honestly just say ignore that number itself. Instead, focus on the p-value. Right? So p-value has that benefit of it is universalizably interpretable, right? So we use that 0.05 standard. In this case, our p-value is less than 2.2 times 10 to the negative 16th, so an extremely small number. So whatever this thing is testing, we're going to reject the null hypothesis. So what is that test? So the F statistic here is testing the hypothesis that all of the slope coefficients are equal to 0. Right? In other words, it's testing that the null hypothesis is that put together all of these x variables, they, they don't actually have any impact on the y variable. Right? So if your F statistic is such that you have a p-value less than 0.05, what that's telling you is that no, there's something in here that does actually matter, either individually or collectively. Now, in our case, we only have one x variable, so you're going to find that when that's the case, your p-value for that x variable's slope is going to be the same as the p-value, right, for the F statistic. In this case, the only reason that it looks different is that there was some rounding that happened up here, that point 2 where it got rounded off, where it didn't get rounded off when reporting for the F statistics p-value. That's the only difference here. But you can run regressions with multiple x's, right? So it's just looking at it's just making a longer equation. So you have intercept plus slope on x1 times x1 plus slope on x2 times x2. But you can have that equation. There's nothing wrong with that. And in that case, right, you might have cases where combined, we know that not all the slopes are zero, even if individually we can't prove which ones aren't zero. And so you could have cases where you have relatively higher p-values for the individual coefficients, but nonetheless a very low p-value for the F statistic. It's kind of rare for that to happen, but it is at least possible. All right. So that is what the output looks like. So in this case, I'd say that this is a pretty good regression in that F statistic is has a p-value that's very low, showing that this is a statistically significant relationship. The R squared is quite high, which indicates that it's very useful. Right? So I can really think of it as F statistic test is the relationship real. R squared test is it reliable? Right? So that is, are we going to get good predictions that we can actually rely on as being reasonably close to correct? And then we can also see the specific details from the coefficients themselves. Okay. So let's suppose we want to do some prediction with this. So how do we do that within R? Now, one thing you could obviously do is pull out your calculator and just start punching in numbers. That works. But I don't want to do that. Instead, I'm going to do two steps here. So first to set up the prediction, right, and then to make the prediction. So to set up the prediction, the first thing we need is we need a data frame that has the same general format as the original data frame used to create the regression. Specifically, we need to make sure all the x variables are in there and are named exactly the same way. Easiest way to do this is what I'm going to do right now. That is, I'm going to make something called new data with an underscore there. That way it knows, because there's also sometimes you have to set a parameter that's new data without the underscore. So I want to make sure that R knows what I'm doing. So new underscore data, I'm going to assign to that from the data frame the first line in all the columns. So it's just VF bracket 1, comma, and that's it. Then what I'm going to do is I want to edit that. So new underscore data. Again, the assignment operator, if I can type, I'm going to use edit new underscore data. So what this is going to do, it's going to open up an editing window, which you can treat very much like Excel. And you can just type numbers into it. All right, so that's what we're going to do. So first thing it does is create new data based on the old data frame. So that way we get the right variables. And then I'm going to edit that new data, which allows me to type in the x's that I want to make predictions for. So I'm going to go ahead and do that. So run that chunk, and it should, right, open up a window that looks kind of like this. Right, so we have here my Canton unemployment rate, and it just pulled from the first line, so the 6.1 is there. U.S. unemployment rate, it pulled from the first line, so I have the 5.6 there. And then it also, apparently there were a couple blank variables that also came in that spreadsheet. Okay. So what I'm going to do, I'm going to modify this US unemployment rate so that it is what I want it to be. Right? So rather than it being 5.6, I want to first have multiple lines and not have it just be 5.6. So I'm just going to put in the number 0. Right? Next line 1, 2, 3, 4, 5, and 6. So what I'm going to do is then come up with a set of predictions for each of those US unemployment rates. So what would Canton look like if the US is at 0, if the US is at 1, if the US is at 2, 3, 4, 5, and 6. So I'm going to have 7 different numbers here, 0 and then 1 through 6. Okay, so once I have that all edited, I can close out of that window, and that should save it. So let me double check that because I have trust issues to be honest. Okay, so pulling up the new data here, you can double click on it inside of the RStudio environment. And it looks like, yes, it did in fact modify it the way that I wanted. Fantastic. All right, so now very important that I not run that code again, because remember what that line, in my case, it's line 25 does, that's going to take new data and then we'll overwrite it with whatever that first line of the data frame is. So I don't want to do that. Right, so I'm going to start then in a new chunk where I'm going to actually make the prediction. So the function here is just called predict. And then you tell what object to use. So we're going to use that regression, lm.r, and then new data equals new underscore data. That's it. All right. Now I will say right now, right, at this point, this is the reason I had this is my second try making this video. The setup up here is extremely important. If you left those DF dollar sign here and here, this is not going to work. All right. So just keep that in mind. Right. So if for some reason this gives you weird stuff, that would be something to check. All right. So let's go ahead and run it. What do we get? There we go. Right. So this is now note what it's showing here is the line number, not the X value. Right. So remember that first line was a 0. So if I have 0% unemployment in the US, we'd have predicted 0.384667 right there. Right. Now, another thing we can do with this, I'm going to go ahead and add another line here. I mentioned before that you could actually do intervals, right? So I'm just going to go ahead and do that as well, just so you can see it. Right, so you can fill this out. So it's lm.r, new data equals new underscore data, and then interval equals prediction. Uh, might possibly have to be predict. Honestly, I don't remember off the top of my head. Oh, yes, it does it. Perfect. Right, so in this case, what it's showing me here, like, what is the best fit? And then it's also showing me what are the upper or lower and upper. So this is in effect like a confidence interval, except a confidence interval is about the average. This is a prediction interval. So this is actually applied to the individual observation, right? So if we have, say in this case, I know that was a 4% unemployment rate in the US as a whole, this would be our best guess for what Canton's would be, but we're 95% confident, right, that the individual value is going to fall somewhere between 2.81 and 6.27 or so. So it's a fairly wide interval. Now you could also replace interval here. Instead of prediction, you could use confidence instead, in which case what you'd get there, the lower and the upper would be the range for the 95% confidence interval for the mean. Right? So on average, whenever the US has a 4% um, a 4% unemployment rate, then this is what it would be in Canton. You could do that. Prediction interval is about the individual observation. That is that for what regression can do. I hope this was helpful, and have a good one.